Hello students, in this video we're going to derive the expression for a Taylor polynomial. Now remember, a Taylor polynomial is a polynomial approximation to a function f of x at an expansion point, and we'll call that expansion point x naught here. So what we want to occur is we want the polynomial to be exact at x naught. Of course, we want the derivatives, all its derivatives, to be equal to the derivatives at x naught as well. I have to put a little prime there. Okay. We're going to have some assumptions here that f is continuous and has n continuous derivatives, and x naught is going to be in the interval where f is continuous. So what we do here is we write the polynomial so that it has is of this form, a naught plus a1 times x minus x naught, and so on and so forth. And I should put a little 2 here. Okay, and you'll see what's going to happen here. If we want to determine the a naught, the a1, and the a2, and all the way up to the an, this will be an nth degree polynomial. But notice that we have there's actually n plus 1 terms here, right? Because we're indexing here at 0. So if n were 3, there would be this n would be a 3, and we'd have 1, 2, 3, 4 terms. Okay. Sometimes the a naughts, the a1, a2, sometimes they'll be 0, and sometimes they'll be non-zero. But anyways, let's determine them, and then we'll get an expression for the Taylor polynomial. So let's do this for a third degree polynomial, and then I think you'll pick up on how the pattern works. You'll notice that if we take x naught and we plug it in to the polynomial, as I had on the previous slide, what'll happen is you'll get x naught minus x naught, and that'll be 0. So this term will cancel. X naught minus x naught will be 0. This term will cancel. Then this term will cancel for the same reasons, and you'll be left with a naught. So a naught is equal to p3 of x naught. But remember, we wanted that to be exact. We wanted that to equal the function at x naught. So we'll get this kind of expression. P3 of x naught is equal to f of x naught, and just as I said before, all these terms go to 0, so that implies that a naught is equal to f of x naught. Now, remember the condition I mentioned earlier, that we want all the derivatives to match, so we'll use those conditions to derive the other coefficients. If we differentiate this polynomial, the constant is 0. The derivative of x is 1. This is a constant, so that's going to be 0. So the only thing that survives is a1 in this expression here, and that's why we get an a1 there. We'll have a 2 times a2 x minus x naught, then we'll have a 3 times a3 x minus x naught squared, and then so you'll see that expression down here. And then if we plug in x naught, we use the same strategies we did in the previous case. All these terms will go to 0, and we'll be left with a1 is equal to f primed x naught. Now, if we do this again, we take a second derivative, then this term will be 0, and we'll get a 2a2, and a 2 times 3, a3. So I'll leave it like that. I won't write it as a 6, because you'll start to see a pattern here. And if I solve for a1, I'll have a1 is equal to f prime of x naught, because all these terms will go to 0 if we plug in x naught. Then the second derivative, for the same reason, the second derivative at x naught will result in this term canceling. We solve for a2, and we get 1/2 f double primed x naught. And then similarly, a3 will be 1 over 2 times 3. The third derivative applied at x naught. So hopefully you've picked up on the pattern. You can see the strategy here. We can just generalize this by an induction, and you'll see if we put all these things together that P3 is, this was the A1 sorry, this was the A0, the A1, this was the A2, and this was the A3. And what I've done here now is I've just written these terms with factorial notation. Recall that 3 factorial is 3 times 2 times 1. And if you wanted to put a 1 factorial under there, that's still going to be 1. You could put a 0 factorial under this term, but remember that 0 factorial is 1, and the reason that this term here does not have an x minus x naught is because that's x minus x naught to the 0 power, and remember x minus x naught to the 0 power is simply 1. So anyways, if we generalize this, then we get this polynomial here, and this is the sum that I had on the first slide, where we're taking the, when k is 0, we'll be taking the 0th derivative, which just means we get f of x naught. If k is 1, we're taking the first derivative, which we see here, and that's divided by 1 factorial, x minus x naught, and I should have a k here. And then we just keep going on, and you'll see the pattern here. So if k is 2, we have a second derivative here, and that's 2 factorial, and that's squared, and that's squared. If k is 3, we'll have a third derivative, that'll be 3 factorial, and that'll be a third power, so on and so forth. Now the question we want to answer is how well does Pn approximate f of x near x naught, and we need to focus on these two terms. How well, what does that mean? How good of an approximation, and how near is near, okay, or how close is near. We'll cover that in another video. All right, good luck.